So the evolution of Android graphics. I think I'm kind of uniquely positioned to give this talk because I've been at the Android team for a really long time. I've kind of watched a lot of this stuff happen. I've worn many hats, many of them quite silly. I've been to many places. And so let's talk about the agenda for here. We're going to talk through some ancient history. I'm going to talk a little bit about RenderScript and what we're doing with it, a little bit about accelerated rendering in general, how things are evolving, and I'm doing the thing of reading all the bullets on a slide that you can read, so we'll just continue. We're going to get into cool stuff like how to blurry mandrels and other graphic-y things. But let's go back to ancient history, and this is fun. Just this is what the website used to look like for all those people who were there, like in Android 1. This is actually Android 1.1, but it's close enough. It all looked like that. And in the beginning, what did we have? We had OpenGL ES 1.0, which we sometimes didn't even have hardware support for. So we had this thing called Pixel Flinger, which a genius wrote, which just basically converted. It was an in CPU GPU. We had fixed point. We had immediate mode rendering. Lots of artifacts. And in the beginning, we had this thing called shader, from day one. This concept that you could take things on the canvas and you could draw them with something that would actually do cool effects. And you could do gradients, and you could do textures, essentially, with a bitmap shader. You could compose multiple shaders together and do kind of pretty interesting things, especially given that we're talking about something that didn't even necessarily have any kind of GPU hardware, so to speak. And this was all done on the CPU back in those days. So a pretty cool piece of software. And this is what that architecture looked like. So you either were drawing on canvas, and then you were drawing through the Skia graphics layer, and you would draw onto your surface, or you were drawing using OpenGL ES 1.0, and you're drawing onto your surface. So this is really simplified, but that's what things were like in 2009. And then we introduced RenderScript, which was heterogeneous compute and graphics, and we did it for this as much as anything else. If you ever remember these early things, for those of you who've been around, I'm my old man now going, oh, back in the days, when the Claire came out and we had the Nexus 1. This is kind of where we're at. And we did this because we wanted to have a way for performance and compute across heterogeneous hardware. Because we had a lot of different chipsets and ABIs, and so this wasn't actually public as in the Nexus 1 era in the Claire, but we eventually did make it a public API in Honeycomb. And we then added, in Jelly Bean, we actually took away the graphics functionality. You used to be able to call OpenGL directly from RenderScript. We took that away, and we added a GPU backend, however, so it was accelerated in some cases. And we also added these Intrinsics, which is probably, how many people here have used RenderScript Intrinsics, by the way? Just from a show of hands, okay. They're probably the most useful thing that we ever did with it. We added a intrinsic for blur and YUV to RGB conversion and a bunch of other things that are useful. They're pretty fast optimized code, despite the fact that they're running in RenderScript as much as anything else. And then in Android 3.0, we had to bring Android to tablets, and so we created something that we call HWI. And this is basically because this is from one of Romain Guy's talks. If you look at our pixel count versus our memcopy performance, we actually got slower memcopy performance on the zoom, and we had a lot more pixels to draw, and it basically meant that everything we were doing before didn't work at all. We had to have actually, do something else. So this is what we did in 2001. So now we have this thing called HWI. It draws using OpenGL ES 2.0. We had Skia, which was still drawing straight using the CPU, and everything hit the service. By the way, everything was always composited on the GPUs. People always said, "Oh, you didn't have GPU acceleration until this point." We didn't have GPU accelerated drawing until this point. Let's just make that a little clear. And here's how it basically works. And it allows for accelerated rendering. It also introduced a new animation system that could take advantage of this. It's pretty cool. It basically creates a display list. And we finally eventually added this API called RenderNode that allows you to get access to the display list, but for a while it was just an internal concept. And this is nice because basically when a view gets invalidated, its display list would get updated and display list could get updated, but all the other views didn't have to update, and that prevented a lot of traffic from going on. And that's how pretty much fast rendering works on Android today. Even if you're using Compose actually directly interacts with these display lists. And Honeycomb was particularly challenging because we actually added gradient backgrounds on lists, and this meant we had alpha blended list items and all sorts of things, and so we had to create layers. And we always had layers to a degree, but we made them a little cleaner, and we got rid of this thing called set drawing cache enabled, which I think was actually an API that people understood, and we changed it to set layer type, which actually does the same thing but adds a little more functionality. So if you want to cache your scene, your layer today, you actually use set layer type. And we wrote our own accelerated renderer, and I can say Ramangi wrote most of this. He pretty much spent sleepless nights for weeks doing this, and he got most of it done in Android 3.0, but there's a lot of stuff that wasn't done. We kept adding more things to it basically as we went along, and we added OpenGLES 3.0 as we got to Jelly Bean, and then we even added more stuff in 4.3, and then we added Vulkan. So again, this is nice history here. And then in Android 9.0, we finally added some of the things that people really wanted us to be able to accelerate, like draw vertices. This is because we actually brought Skia back. So after all that time, we were building HWUI completely in parallel to what was going on in Skia. Meanwhile, in the world of Skia, which is used in Chrome and it's used in a bunch of other places, they actually were also working on their own accelerated rendering path. And so in Android 9, we smashed them together, and we got all of this other cool stuff kind of sort of for free, and it mostly works the same. And hopefully, as developers didn't notice this, that happened if we did our job right. You might have noticed certain things didn't perform quite the same. Some things perform better, some perform worse, but we kind of did it sneakily, and so this is what it looks like today. It's gotten again a little more complicated now. And this is the OpenGL version. It actually works on top of a Vulkan backend as well. So we also got that from the Skia team. And so this is basically how it kind of works today. We now have a render thread, and so one or more views basically draws into one of these render nodes that I was talking about. This forms a tree structure. You think like one render node per view, or per composition. They store matrix information, a list of drawing commands, Z-order, and a few other pieces of information. And it basically is all designed to make invalidation really fast. Parts that don't change use the same render node from the previous frame, and it simply just records its pointer into the list. And because we have this render thread, we have a couple of interesting things, like we have two copies of data structures and stuff like that. So if you ever see the way like the classic ripple animation works, that's actually running on the render thread. That's one of the reasons we ended up building it. So yeah, it's complicated. And then in Android 10, we actually upgraded to Vulkan 1.1, and so this actually allows us to use Vulkan, and hopefully eventually Vulkan everywhere. So you think about Vulkan as a very, very low-level graphics API, and the idea being that at some point we have this thing called Angle. Angle is actually how we run WebGL on Windows. It's a general API that allows different low-level APIs to target OpenGLES. So basically, we wrote a version that sits on top of Vulkan, and in the future, this might be what our stack looks like. It'd be really nice if that happened. In Android 12, we deprecated RenderScript, and this was sad because, like I talked about this earlier, RenderScript was actually pretty cool, but honestly, OEMs weren't supporting it really well. Lots of places didn't actually have accelerated support for it anymore. People were looking for an accelerated API, and they thought it was there, and then they would run it, and it would work on some devices and not others. And we had to make a difficult decision. Did we try to port RenderScript on top of Vulkan ourselves and build and spend a huge amount of time and effort doing that, or did we actually try to focus on just making everything else work really well? And we decided to focus on making everything else work very well. So RenderScript is going away. It'll still work for quite a while. It's just not going to be accelerated. And then getting to Skia is actually pretty cool because it actually allowed us to think about evolving graphics again. So in Android 10, we really were able to move graphics forward. And we added this thing called HardwareRenderer. We added access to RenderNode. We added this thing called recording canvas and surface control. And this is for the first time, this allows you to actually go and hardware render something into a bitmap, which you couldn't do before Android 10. We also added NDK features like surface control and surface transaction stats. So lots of really cool stuff ended up in Android 10. Android 11, we added support for the NDK for a lot of things we did in Android 10. When we added an actual image decoder for a long time, we had like a couple of libraries that you could use, but we actually now have a proper image decoder for NDK. And then we started really actually thinking about how we evolve this platform more in 12 and 13. So in 12, we added this concept of RenderEffect, which allows you to go and apply one of these kind of built-in shaders to a render node. And then the thing I'm most excited about is in Android 13, we finally made programmable shaders happen. So that thing that we talked about in Android 1.0 of this concept of having a shader that could shade anything that you're drawing inside of an Android canvas, we finally now allow you to write your own shader and do whatever you want. And that's pretty cool. So what are we doing to replace RenderScript? Well, this is kind of what you have to do if you want to have like true hardware accelerated compute guaranteed to work on any Vulkan device. It's actually nice because Vulkan's really complicated. Has anyone here programmed Vulkan before? Show of hands. I've programmed it a little bit, and the famous thing is it takes like 10,000 lines to draw a triangle, and that's not quite true, but it is really complicated. There's all these different stages you have to deal with. But those are for graphics. But if you're actually talking about compute, it isn't actually an API that has a lot of extra overhead. It's not a lot of stages. You're basically just doing what the minimum you'd expect a compute API to do. And so I actually like it as a compute API if it suits your needs. It doesn't do everything that some of the kind of like OpenCL 2 does, but if OpenCL 1 level stuff suits your needs, then Vulkan's actually not a bad choice. And again, this is what the compute flow looks like. Again, it looks complicated, but it's really not. You need to do all of this stuff in compute. You need to know what hardware you're running on. You need to know how many kind of virtual threads you have. You need to be able to allocate a command pool, and then you need to kind of submit your commands and wait for them to get executed. So like this is actually it's not that complicated, and this is pretty much any compute API is going to look something like this because you're ultimately designing a compute kernel that's running across a whole bunch of multi-threaded hardware. And we do all that to run this little shader. This is just a color matrix thing you can use to rotate colors. We also have the same thing built into the platform. But this is just an example of like, you run all of that stuff, and this is actually the code you're writing. So all that other stuff is pretty much largely boilerplate for a lot of what you might end up doing. So that's the kind of cool news here. But you can tweak it all to really do pretty fantastic stuff. So what we have is a pretty cool RenderScript migration guide and sample that one of my colleagues wrote. It actually implements that whole thing that I talked about in this sample, and so you can actually see how it works with multiple different things. He implements color rotation and blur, and it works on. It uses Vulkan. It also actually uses OpenGL, and it also uses RenderScript as well as RenderScript Intrinsics. So it's actually pretty cool. You can see how all of these things kind of relate to each other. Another thing that's kind of cool is there's an OpenCL to Vulkan compute shader compiler. So if you have something in OpenCL, you can try playing with it and see if it actually does what you need. A lot of times you want to, you don't want to have to write these things for every single platform. So it's a way of potentially helping you with that. And so this leaves us with this thing. What do we want to do for best performance compatibility? We want to use RenderScript targeting less than Android 10 and use Vulkan for Android 10 plus. We've also written this thing called the RenderScript Intrinsics Replacement Toolkit. This is basically, we took the Intrinsics and we pulled out all the CPU optimized versions of them. It's an open source NDK project, and it's actually really, really fast. Like, it turns out that a lot of those Intrinsics, they were these very tight written, largely assembly code, and it took longer to churn up the mechanism of RenderScript to actually run the kernel and do all of this stuff than it did to actually execute the intrinsic. And so it turns out in many cases these are actually way faster than running them within RenderScript. But for a few things we have RenderEffect, and basically, this is, if you're using views, or if you're using Compose, you can easily use RenderEffect. In views, you just call set RenderEffect on your view. In Compose, you actually can create a modifier on your graphics layer that again is a RenderEffect. Remember, ultimately Compose is just sitting on top of, for the most part, and this is like a very gross simplification, but sitting on top of render nodes. So this allows you to get access to that, and you can apply these kind of effects there. And this is if you want to apply the effect to the entire screen. The other cool thing about doing it this way is you can actually do it you can actually create like blended graphic effects on top of what Compose is doing. So you can get the pixels that Compose would normally be putting on the screen, alter them in one of these shaders, put them back out. It's pretty cool. It's great for blur, which is commonly what you'd want to do. You want to blur your entire background. You want to blur the entire display hierarchy below you. So it works really well for that. So basically we call set RenderEffect, or as Compose RenderEffect, and that's how we do it. It ultimately generates bitmaps. And if you're using the RenderScript intrinsic, so what we can do is use this feature that I was talking about before, this RenderNode hardware renderer thing, which we introduced in Android 10. And you can basically say, I want to set a surface to my image reader, and as long as it supports like this particular kind of image reader, which has to be this hardware form, then you can just use the hardware renderer on top of it. And this is pretty cool. So now we're actually using GPU hardware to render into a bitmap, and you can make it totally compatible with what you would do with something like RenderScript. So this is a way to say, hey, I want to use RenderScript to do something in one version, and I want to use AGSL, this shading language, in a new version. So then we have to render it. So we use this thing called a recording canvas. We actually render a bitmap, and then we create a render request. And this is, if you saw that whole pipeline chart before, this is now where we've thrown it into the GPU pipeline, and we're just waiting for the response. And then we do this to actually acquire the image, and we're done. So this is then what we do. This is actually we just create a color matrix, and we create a color filter effect, and we're there. So that's that, and that's how you can use like the built-in shaders and do something that's kind of cool. But this is actually, I think, my favorite thing. As I said, I've been waiting. I've been on the Android team for 12 years, and I've been using Android way before then. I've been waiting to be able for programmable shaders to happen this whole time. So now you can finally do it. So first of all, when we're talking about a shader, we're talking about a fragment shader. And this also, a lot of people call these pixel shaders. A fragment can be a little bit more than a pixel, but usually it is, to dramatically simplify things. And in certainly all the cases that I'm talking about here, fragments and pixels are the same thing. And this is a shading language. So it's a language that looks a lot like C. It has a low-level support for things like vector and matrix data types, and all sorts of things that are really cool if you're doing graphics that are just like there for you. And it has a very compact syntax as well for all of these things. And it basically executes largely on the graphics hardware. So I'm going to be putting up a whole bunch of QR codes. If you want to see, you can try these on your phone. These QR codes will actually take you to our Skia graphics playground online. So if you want to snap any of these, this is like the first shader that I ever wrote that does something slightly more than just draw like a gradient or something like that. I wanted to draw a graph to show the difference between AGSL and GLSL in terms of the way they work. So this is like about as simple as you're going to get. It just draws a grid. It actually tries to draw the correct number of horizontal or vertical squares, and then divides it up into the minimum number of squares to draw. And it's pretty simple in terms of code. You can take a look at it. I'm not going to explain how this works right now. So I want to get back into this color effect that I was talking about. So again, a color rotation effect is pretty easy. It's something that's built into the platform, so you don't actually need this. But I wanted to kind of walk through what it might look like. One thing to note is that shaders are really, really fast, and they run completely parallel on the GPU. And that means that you cannot have dependencies between them. So you can't have one shader modify something that another shader is doing in a single pass. You can do multi-pass rendering and stuff like that. But basically, you're stuck with this. In order to make it so that I could actually modify the rotation without having to recompile my shader, I actually calculate for every single pixel on the screen this entire rotation matrix. And so we start off with these things called uniforms, and uniforms are how you get input into a shader. So basically, otherwise to do anything in a shader, you have to recompile things. That's kind of slow. So this way we can put parameters in. And some of these things are kind of useful, like resolution. Normally, the only thing you get from a shader is what's the fragment coordinate that I'm shading, which is essentially the pixel. But you might want to know where that is in terms of the screen, so passing in the resolution is really useful. This also has the image resolution because I'm actually working on a bitmap, so that's kind of useful. And then it has the radian that I'm using to rotate. So one other thing to note about this is that in AGSL, there is no way to directly sample a texture. So what we're doing is actually creating a bitmap shader, and we're pulling that in and we're sampling that, which is almost like sampling a texture, but just kind of a little side note there. It could be any other shader. So you can sample like a complex shaders. You can make things that are way too complicated to actually render in real time really easily here. Again, we get this fragment coordinate, and then we evaluate this thing. And all we're doing from each one of these shaders is returning the color of the fragment that's being shaded. So again, the output of this is basically for every single pixel we're drawing, this thing is going to return the output. And it's returning the output based on a sampled bitmap. And again, this is this rotation matrix. And again, this just shows how fast GPUs are. The fact that I can calculate this for every pixel, and the GPU is like, whatever. And this is again, there are 15 lines to this. I just didn't want to put them all on the screen. So we apply this the same way. We have to set uniforms. So we've got, again, image resolution. I'm just using the bitmap here that we're rendering to, the float uniform, which is what we're using to rotate things. And then we have to actually have this input, this bitmap shader. So we got to create that, and we've got to, in this case, set the tile mode and various other things. And then we actually create the effect. And this actually, at this point, does all the magic. If you want to see how this works, not on Android, but on WebGL. And by the way, this playground is like one of those things that's kind of the miracle of like multi-layered architecture. This is actually running Skia, like real Skia, which is like a C++ thing, compiled into WebAssembly, running, which is then targeting WebGL, and it all works, which is kind of mind-blowing to me. So if I click on this, it should be able to take you right there, and you can use your mouse to click through this, and you can rotate the matrix. So yay. I'm just using the X coordinates for that. So that is what this demo is. Unfortunately, the mouse stuff doesn't seem to work right now on phones, so sorry. So that's all that demo is. All right, let's go back. And again, we can apply that to a render node just as simply, and that applies it to the node and its parents. Now, that's cool, but that's actually pretty expensive to apply the shader to the whole render node. And you don't need to a lot of the times. You just want to shade individual pixels. And so we can do a lot of these things with less overhead. Plus, every time you create a new render node, you are also, by definition, creating a new hardware layer. It's actually pretty expensive. So it's much better to actually just if you could just use the shader to shade things in Skia, and you can do that by doing a custom view on Android and drawing, and core Android and drawing it. But what's really fun is that Jetpack Compose makes it super easy to get access to a Compose canvas. And shader brushes are built into Compose. This actually works on Compose Desktop and on Compose for Android, because Compose Desktop just happens to use Skia as its rendering layer. So it's pretty nice, and it makes it really easy to get access to this. Like where before I had to go and build a custom view and then have it paint like this, I just say, yeah, I just want a canvas. And it's even easier with Compose 1.2 because you can actually select a shader brush for text. And again, shader animation with uniforms is pretty cool. Like we want to then go and say, how do we animate something? So we can use, like we'd expect, we create a value animator. We set its duration, and we use that in an update listener to set the float uniform. And that allows us to animate something that's inside of our shader. We're literally just updating values in our shader over and over again. We can create really complicated animations with that. So this is my gradient. This is the very first animation that I ever did inside of a shader, so yay. As you can see, we have this, we're just sending this parameter over and over and over again to the shader. Again, like with all these demos, you can click on it and see what it looks like inside of this beautiful playground that we have. And this playground also has a built-in debugger and a few other things. So it's actually a really nice way to write these. Although I have written them in both ways, written them on device or there. And then we can also apply this again to anything that accepts a brush. So you can paint text either with Compose or with standard views, just like that, and do really fun things there. And you can mix all the regular animations you can do. So this is using an Android camera to create a pseudo 3D effect of that text, and we still have the animated shader going on inside of it. So that's an example of how. And what's really cool about this is that again, it exists within the regular Android rendering pipeline. It's not something that's separate. You don't have to set up a whole OpenGL context or a surface view or anything like that. It just works. And again, we have this cool thing at shaders.skia.org that allows you to debug it. And Skia is an SKSL, which is the shading language that's built into Skia, is almost the same as AGSL. By almost, like, we took a few things out, honestly, for Android that we weren't sure we wanted to support, but it's almost identical. So yeah, also this is what that mandrel shader. This is I wanted to do a blur shader basically. By the way, you should never do a single pass blur shader like this. This is way slower than the multi-pass version, but in order to run something in this environment, you need this environment doesn't support multi-pass shading. So that's just an FYI. It actually runs not so bad, but this just shows you can do even fairly advanced image processing. Not that blur is that advanced, but it's surprisingly tough. Just in this kind of environment, and it's a nice thing if you're already using something like RenderScript. You want to replace it, you want to do other things. There's actually, if what you're doing is particularly targeting stuff that's going into the UI, this is a great way of doing it. You can use it, again, to generate a bitmap, and you can use it for actual image processing as well. At that point, you might want to think of something else, but I think it works pretty well in that case as well. And just to show you, you can port, there's this site called ShaderToy. How many people have ever seen ShaderToy, by the way? All right, well, it is really fun if you want to waste like an entire afternoon. Go to ShaderToy and just click through things. It's amazing. And many of these things can be ported with very little work from ShaderToy. This is an example of a star field animation that's entirely done in fragment shaders that's been ported to AGSL. And there's tons of other stuff there. But let me get to a demo that I spent a lot of time hacking on. So one of the cool things about when you actually have access to the resources of the GPU is you can do more than just 2D stuff in here. So this is something that actually was built originally by a guy named Simon Green, and he did amazing work. I wanted to take it a little further, so what you're seeing here are a lot of androids. And what I wanted to show you is just how simple the shading language actually is. So this includes all of these parameters that I can use to tweak what's going on. But you see this entire shader right now is 443 lines, I think, long. So this is not a lot, and that includes all of the artwork and everything you're seeing here. And this is using something called ray marching, which is a way of doing ray tracing in kind of a fairly efficient way, entirely running inside of a fragment shader. It's just using math. So the head is a sphere, which is done using what they call a sign distance function. And that's how kind of ray marching works, is basically, you can imagine for every single pixel, we cast out a ray from an origin, and then we march down like these kind of spheres in order to figure out where it actually intersects with geometry and what pixel color needs to be. This has a couple of different materials that it's using. There's a material for the eyes, there's a material for the floor, and then I have a lot of fun with like just making a bunch of custom materials for each one of the droids. I wanted them to all be there. Another thing that's interesting is that it looks like there's a ton of geometry here. And this is an example of how you can fake things in computer graphics. With a sign distance function, basically, you can use the modulus operator to repeat the same thing over and over again. And this is repeating the same exact geometry, sort of, across both X and Z axis. And so that just makes it look like you've got this infinite plane of androids. But actually, when it's calculating each individual pixel, it's only calculating a single android for each one of those pixels. And that's part of how this gets to be so fast. And how you can do things like have the androids all reflected in the surface. Because this entire scene is actually calculated multiple times. It's calculated once for the to know the distance. It's calculated again a whole bunch of times to calculate what they call surface normals in order to figure out how to shade things. And it's calculated all over again to do the reflections. And that's all happening inside of the GPU. This does not run at full speed at full screen on a Pixel 6 Pro. Let me just say this. So I can show you a little bit of what we can do there. And what's fun about this is that it's all, thank you. It's all parameterized. So one of the things we can do is we can, I'll just show you. Let's get rid of that modulus stuff here. We can get rid of all those other droids. That's actually closer to what's actually rendered. We can also stop animating it, so we can take a look at our 3D model a little bit here. I'll stop animating the arms. The arms are actually, the reason the arms can swing like that is that they are animated with a sine wave, and they're simply animated in a different relative position of the sine wave. So that's like a trick to use even though this guy is normally symmetric. And if you look at the actual way this is rendered, we actually have, this is the scene, which is again turns the whole thing into a single mathematical equation, which is a really nice way of abstracting it. This is actually, this one statement here that says absolute value here is actually how it takes advantage of, takes advantage of symmetry to actually render the Android. If we get rid of this, you'll see this is actually what we've defined mathematically. So we're taking this all down to its kind of base here. There's a lot of things that kind of fall out of this that we can do here. I don't want to. Please go and play with this. I'll put up the QR code again. Have fun with it. But just to kind of show you a little bit of what the kinds of things and how mathematically defined this really is. This is just, again, I said it's a modulus which is used to represent the way we repeat things. So we'll turn repeat equals true back on, and then we can change our modulus, which basically is like how often we're repeating him. So we'll change it to 2. And now we're blocking the camera, and there's a lot more of them. We also can make them varied shapes. So let me kind of show you there. This is one of the things I did was I parameterized the Android so that he can be different shapes. Let's also move the camera a little bit up so we don't have the camera getting blocked all the time. All right, so so again, right now they're all the Androids are the same. I felt that was a little bit like Big Brother sort of thing here. So like that goes kind of against our whole model here. So I took the Android model, which again is just a mathematical model, and I very cheap is true. And I took this and I said, okay, let's parameterize this so that the androids can all be different heights and widths and colors. The other thing is that the colors are actually just spread across the hue spectrum, and I can create as many colors as we want. Right now I've got 8, but we can create 12 colors. That's kind of pretty, or 16 colors. And again, all I'm doing there is taking the androids and I'm spreading the color across each one as I'm modulising these things across. And again, I can control things like the eyes and all this kind of stuff. I had a lot of fun with playing around with math and making mistakes throughout all of this, like any kind of programming. But when you make a mistake here, sometimes it's actually kind of fun. So this was a mistake that I made here. When I was trying to get them to be different colors, I didn't do the math right, and I thought, well, that's kind of cool. I should keep that around. Doing this kind of effect would actually be really, really hard in like a regular geometric scene. But in this, it just kind of falls out of the way it's being drawn. So I hope this was a little bit inspiring. There's a whole bunch of other things on the Skia site here that kind of give you an idea of the kind of wild things that you can do with these shaders. It's a really cool capability that I'm really happy we finally added, as I said. And it allows you to run these things on the GPU. This is actually a fractal cloud, multi-level cloud simulation. If you look really closely, you can, I think, see a little bit of the Julia set in there. But you put enough noise in, and it's pretty fun. And honestly, go to ShaderToy and take a look at it, shadertoy.com. There's just an amazing amount of stuff in there. Because those are all owned by different copyrights. I don't want to put them up in this talk, but this is actually a Julia set here. But there's just a lot of really, really cool things. And just, you can add all this stuff into anything you're drawing. So let me just do one final thing before I go, and say, yes, this is actually running in the Android emulator right here. The exact same thing that you saw me playing with, all the same parameters. I've simply used a raw resource for the GLSL file, and thank you to one of the plugins that I have for Android Studio that colors it properly so that I can edit it more easily. The final thing I wanted to say is that yes, this is just like you'd expect. This is, let me get that code out of the way, although it's kind of fun to have. Just like you'd expect, this is running right within the entire framework. So I can take this and I can use this as a brush to shade anything I want. So this is an example of using that same shader that I just wrote as a brush within Jetpack Compose to shade a piece of text. Now, this is not necessarily the most useful thing to do, but I just wanted to kind of show what the possibilities are. And again, all of the Compose animations, everything you do, all can work on this same thing that we're drawing, and to me, that's exciting. And this is, again, there's absolutely no magic going on here. This is all just a fairly complicated shader. It's running on the GPU, and it actually runs relatively well on real hardware. So it does run a little bit faster on this laptop. There's some other fun tricks to do there. But I just wanted to kind of show what's possible, and I think that as Android 13 gets more and more adoption, it's going to be fun to see what people do with them. So that was pretty much all I had for my talk. So here, just kind of leave you with things. Actually, I want to do two things. One, I wanted you to go back to anyone who wants to play around with this particular demo. Here's the QR code. Go play around with all those parameters. You can see most of them work, but you can break it. Don't use this as an example of exactly how to do this technique. It's pretty hacky in places. One of the things I end up doing is it uses a ray marcher for all the androids, but the floor is actually done with a raycaster, because doing an infinite plane and a ray marcher doesn't work all that well. So there's a lot of fun stuff in there, but definitely play with it, enjoy it, and it's even better on a laptop playing with this thing. So things to remember: if you're using RenderScript, use it for compute. If you want to target less than Android 10, consider using RenderScript. Still, for Android 10 Plus, Vulkan has a lot of stuff that it supports. And you can also use AGSL for effects that can be expressed in a shader. So you can do a lot of really cool image processing in there. RenderScript in Intrinsics, we've got this cool toolkit on GitHub, which you do have to build, unfortunately. But it actually it takes all that really fast code, this optimized assembly language code, and makes it really, really easy to use and keeps it really fast. Camera X now supports YUV to RGB, so a lot of people were using RenderScript to do that, and the good news is you don't have to anymore. And plus, RenderScript actually didn't support the YUV mode that our camera supports anyway, so it was kind of hacky, and there is like this piece of Stack Overflow code that's been pasted everywhere to make it work, and it's actually kind of slow, so use Camera X directly. And then, again, we've got this cool playground. There's docs. I wrote the docs on it, so if you hate the docs, just file bugs. I'd be happy to fix them. And that's it. So thank you very much. And I don't know how much time we have left, if any. Like 2 minutes? Okay.